Welcome to a short video presentation through which we aim to highlight the significance of body composition as an indicator of health and well-being. Body mass index is used internationally as a marker of obesity and health risk. Many professionals use BMI in order to rate insurance premiums and even to determine the outcome of residency applications. This being the case, has society placed too much weight on BMI? And what are the alternatives? Professor Marinos Ilia, an eminent leader in the field of nutrition and body composition, will now help to answer these questions.
Obesity is an increasing and growing problem worldwide, not only in developed countries but also in developing countries. It is estimated now that there are over 2 billion people that are overweight worldwide and almost 500 million that are obese. And the situation is getting worse as time goes on, with no signs of it plateauing out. So it is a major clinical and public health problem. BMI is a useful marker for obesity because it can be measured relatively easily. However, it is a crude measure of risk of cardiovascular disease, partly because there are differences in body composition for the same body mass index in different population groups. In certain Asian groups who are particularly prone to cardiovascular disease and diabetes, they express that risk at a lower body mass index than other Caucasian populations. This makes it difficult to use the same body mass index to predict risk in all types of populations. Furthermore, within the same population, there is also variability in body mass index and the percentage fat relationship. For example, those that are active tend to have more lean and less fat for the same BMI. Those that are inactive, the reverse applies. Those that are born low birth weight tend to have more fat for the same BMI than those that are born with a higher birth weight. Overweight and obese individuals put more strain on their hearts. They have higher circulating lipids and they tend to develop insulin resistance. This means that they are more likely to have increased risk of cardiovascular disease, heart attacks, strokes, high blood pressure, and diabetes. One of the ways to overcome at least part of the problems of the BMI measurement is to measure body composition. This can be done by a variety of techniques. Some are sophisticated and require specialized laboratory measurements, but others are simple and could be carried out by the bedside or in the field. Two such simple measurements are skin fold thicknesses and bioimpedance analysis. In contrast, the bioelectrical impedance measurement can be done more precisely in lean and overweight individuals, but particularly overweight individuals. When overweight or obese individuals lose weight or go on treatments to lose weight, it is desirable to achieve preferential loss of fat and preservation of lean tissue. In contrast, individuals that have been malnourished as a result of illness or are entering rehabilitation programs, it is desirable to increase the mass of lean tissue. In both situations, measurements of body composition can help assess the progress that is being made in that direction. The changes in body composition, such as muscle mass, are related to functional outcomes such as strength, ability to work, and other measures. Bioelectrical impedance is a simple method for measuring body composition. It can be achieved using a portable, lightweight instrument and can be carried out in the field, by the bedside, and in various other clinical or public health settings. It essentially measures the opposition of the body to a flow of current The resistance offered by a wire is proportional to its length divided by its cross-sectional area. This corresponds to the height and cross-sectional area of a human body, and from this relationship one can establish bioelectrical impedance equations relating impedance measurement and the height of the individual to the total body water or the fat-free mass. Apart from measuring body composition, bioelectrical impedance has the capacity to do two other important things. One is it is able to assess the distribution of fluid between the intracellular and extracellular fluid, and the second is that it can be used as a predictor of outcome of disease states. At low frequencies, the current does not penetrate the cells because of the properties of the cell membrane, which acts as a kind of capacitor. This means that the resistance at low frequencies reflects the resistance of the extracellular fluid. At higher frequencies, the current increasingly penetrates the cell membrane, especially if the frequency becomes particularly high, and therefore the resistance that is being measured reflects the properties of both the intra and extracellular fluid. It is a marker of total body water. So by looking at the ratio of the two measurements at low and high frequencies, one can establish an index, often expressed as a ratio of two frequencies, of total body water to extracellular water. In disease states, there is often a shift of fluid favoring the extracellular fluid. Indeed, many illnesses can do this, and many illnesses can produce changes in this ratio even before clinical observations suggest the development of changes in fluid hydration. Essentially, the ratio has been used as an illness marker. It has been used to predict the outcome of a whole range of diseases, including mortality. The ratio of resistance at low and high frequencies, as well as other related bioimpedance indices, such as the phase angle, have been used to predict outcome of a whole range of conditions, such as renal disease, chronic obstructive airways disease, AIDS, and cancer. The phase angle is more difficult to understand, and therefore a number of workers prefer to use the resistance ratio. One of the effects of disease states, especially inflammatory diseases, is that they have an effect on the leakage of capillaries to protein. Cytokines, which are activated by inflammatory conditions, cause a capillary leak, and therefore proteins move from the intravascular space into the extravascular space, and with it there is often an associated shift in water. Effectively, this changes the distribution of water favoring the extracellular fluid compared to the intracellular fluid. In addition, in disease states, there are changes in the handling of salt and water, and furthermore, immobility is also an issue, and this can also favor a change in fluid shift towards the extracellular fluid. The sum result is that there are changes in the resistance of at low frequencies compared to high frequencies, reflecting the processes that were induced by the underlying disease process.